Hello there, and welcome to the Celestographer. Tonight, we are going to question something that normally feels impossible to doubt: that you are one person, living one life, moving through one version of reality. Every memory behind you seems to belong to a past that happened only once. Every decision appears to close the door on everything you did not choose. Yet the deepest rules of nature may describe a reality that never closes those doors at all. Somewhere within that possibility is another version of you carrying the same memories, the same name, and the same certainty that their life is the original one. You would never meet them, you would never hear them, and neither of you would feel the moment your futures became different. Tonight, we will explore what this possibility could mean for chance, identity, survival, and the private thread of memory you call yourself. Subscribe to the Celestographer for more calm, long-form documentaries about the universe and the questions hidden inside it. Because the strangest thing about reality may not be how large it is. It may be how many versions of you it can contain. Every morning, you wake inside one world. There is one room around you, one body beneath the blankets, and one past waiting in your memory. The cup beside the bed is either upright or broken on the floor. A message was either sent during the night or left unfinished. The door is open or closed. The rain arrived or it did not. Every detail seems to occupy one definite place in one continuous history. Your memories arrange those details into a single line that appears to have followed you from childhood to this exact moment. Classical physics fits this experience almost perfectly. In the classical picture, objects possess definite properties whether anyone observes them or not. A planet follows a particular orbit. A falling stone has one location and one speed at each moment. A sealed envelope already contains a specific message, even before someone opens it. When information is missing, the uncertainty belongs to the observer. The answer still exists somewhere, hidden but complete. Quantum theory introduces a more difficult kind of uncertainty. At very small scales, the mathematics does not always describe one concealed answer waiting to be uncovered. Instead, a quantum state can contain several physically possible outcomes together. These alternatives are not merely guesses written down because a researcher lacks information. They can interact with one another before any lasting record appears. Consider a single particle moving toward an experiment with two possible paths. A classical object must secretly take one route or the other, even when nobody can see which one it chose. A quantum particle does not always behave as though one path was privately selected in advance. When the two alternatives remain undisturbed, they can combine and produce an interference pattern. That pattern contains regions where detections become more likely and other regions where they nearly disappear. Ordinary ignorance cannot create this effect. Two hidden but independent routes would simply add their results together. Interference shows that the possibilities remain connected inside one shared mathematical description. The state carries more than one future, and those futures can affect what later appears. Then a detector records an outcome. One light flashes, one mark appears, one event enters the laboratory notebook. The observer does not remember a blurred combination of incompatible results. Conscious experience settles around a single record. The room remains quiet. The equipment stands exactly where it stood before. The observer hears one click rather than two contradictory sounds. One result becomes part of memory, while every competing possibility seems to have vanished without leaving a visible scar. This silence is so complete that ordinary life gives no reason to suspect anything else ever existed. You never feel several versions of a morning pulling in different directions. You never carry two incompatible memories of the same conversation. You never experience yourself answering yes and no in the same instant. Your awareness continues as one private account of what happened. Quantum theory, however, still leaves a narrow gap between the full mathematical state and the single result an observer remembers. The equations describe the alternatives and predict how strongly each one contributes. The later record contains only one outcome. The difficult question is what happened between those two descriptions. Perhaps nature truly selects one result and removes the others. Perhaps the mathematical possibilities disappear through a physical process that has not yet been fully explained. There is also another possibility. Reality may never discard the alternatives at all. The full state may continue carrying every allowed outcome, while each observer becomes connected to only one version of the record. In that picture, the universe does not need to make one final choice. The appearance of choice emerges from the position of the person remembering it. Each observer would look backward, and find a complete history ending in one definite event. Nothing inside that memory would reveal that another continuation ever developed beside it. This possibility does not yet prove that reality divides into separate worlds. It only exposes the question hidden beneath every measurement. Why does a state containing several possible futures become an experience containing only one past? For the person living through it, memory remains an unbroken thread. Behind that thread, unseen and unfelt, reality may already be opening like a fan. The wave function is the mathematical object that carries a quantum system forward through time. It does not behave like a private list of guesses written by someone who simply lacks information. Instead, it contains the structure of the results the system can produce, and the relationships between those results before any lasting record exists. That distinction matters because ordinary uncertainty and quantum possibility do not leave the same physical traces. Suppose a single particle approaches an experiment with two possible paths. In a classical description, the particle must secretly travel along one route. Even when the apparatus does not reveal which one, the missing answer would already be fixed. A quantum state can behave differently. The alternatives can remain coherent, which means their amplitudes preserve a precise relationship and can still affect one another. When they meet again, they combine much like overlapping ripples spreading across still water. Some parts strengthen one another, others cancel. The final pattern contains bright regions where detections often appear, and quiet regions where they rarely do. Neither path could produce that arrangement alone. The pattern only emerges because the alternatives remain parts of one combined description. The word wave can easily create the wrong picture. It does not require a visible material rolling through space like water across a shore. The wave function describes amplitudes, and those amplitudes determine how strongly different outcomes can contribute when a measurement is made. Their relative phases control whether the possibilities reinforce or suppress one another. No equation needs to appear on a page for the core idea to matter. The quantum state is not just saying that several answers are conceivable. It is carrying a precise internal relationship between them. That relationship can later change what the detector records. In a dark laboratory, the experiment begins almost without drama. One particle is released. A single mark appears on a screen. Then another arrives somewhere else. For a long time, the detections look scattered and meaningless, like isolated points with no common plan. The room remains still while the apparatus repeats the same preparation again and again. Hours later, the larger pattern slowly becomes visible. Bands of frequent detections stand beside regions that remain nearly empty. No individual particle draws the design. The full arrangement emerges only after many separate events accumulate. What appears one point at a time eventually reveals the influence of alternatives that were never recorded as separate classical paths. This is why superposition cannot be reduced to a box containing one concealed card. A hidden card already has one identity before the box is opened. A coherent quantum state behaves more like a restrained musical chord, where several notes combine to create a structure that none of them produces alone. The comparison is limited because no literal sound is involved. Still, it captures the importance of relationships. Change one component, and the final pattern changes with it. Measurement introduces the next difficulty. Before a stable record forms, the equations evolve the combined state. Afterward, one detector has activated, one result has been stored, and one observer can describe what happened. The probabilities connect those two moments. They tell researchers how often each possible result should appear across repeated trials. Yet they do not, by themselves, settle what the wave function represents physically. Some physicists treat it mainly as a tool for predicting observations. Others argue that it describes something real about the system, even when no measurement has selected a visible outcome. The mathematics succeeds either way. The disagreement begins when the same formal structure is asked to explain what exists. Interference makes that question impossible to ignore. If the alternatives were only unrelated guesses, they could not cancel one another or build a shared pattern. Their amplitudes must remain linked long enough for the experiment to reveal their combined effect. Then, once a lasting record appears, experience contains a single event. The detector does not display a pale mixture of every possible result. The notebook does not carry several incompatible entries on the same line. An observer finds one outcome and builds a memory around it. Early quantum theory therefore faced a narrow but stubborn divide. On one side stood a mathematical description that evolved through several possibilities at once. On the other stood the familiar world of definite records, stable objects, and one remembered result. The equations predicted experiments with remarkable accuracy, yet the transition between those two pictures remained conceptually unsettled. That gap is small enough to hide inside a laboratory measurement and large enough to change the meaning of reality. The state contains several futures. The memory contains one past. Every later interpretation begins with the distance between them. The collapse idea offered early quantum physics a practical way to connect uncertain mathematics with settled experience. Before measurement, a system could be described by several possible outcomes. After measurement, only one result remained in the physicist's record. This sudden change made the theory usable because it told researchers when to stop following the full quantum state and begin calculating from what had appeared. Niels Bohr and Werner Heisenberg helped shape the family of views later associated with Copenhagen. Those views did not form one uniform doctrine, but they shared a willingness to treat measurement as a special point in the description. The quantum state evolved through its possibilities until an experiment produced one outcome. At that moment, the description was updated around what the apparatus had recorded. As a working rule, collapse was remarkably effective. It linked the spread of amplitudes to the single mark found on a detector and allowed laboratories to predict results without first settling what existed beforehand. The difficulty appeared when physicists asked where measurement truly began. A detector is built from atoms. The wires leading away from it are built from atoms. The notebook, the light entering the eye, and the brain storing the memory are physical systems as well. If quantum rules apply to microscopic matter, there is no obvious place where those rules should suddenly stop. One researcher might draw a boundary between the particle and the apparatus, while another could place it between the apparatus and the person reading it. The line helped organize the calculation, yet nature itself displayed no clear border. Erwin Schrödinger pushed this problem into an intentionally uncomfortable form. His cat thought experiment connected one microscopic event to the fate of a living animal sealed inside a box. If the trigger had not yet produced one fixed result, then the larger setup appeared to inherit the same unresolved alternatives. The formal description now included one outcome associated with a living cat and another associated with a dead one. The point was not that real animals are routinely seen in a visible mixture of life and death. The point was that the mathematics had expanded from a tiny event into a macroscopic system without revealing where the special collapse should occur. Outside the sealed box, the laboratory remained still. No movement crossed the lid. No sound explained which result had become real. The table stood under ordinary light, and a researcher waited beside an object that looked entirely settled from the outside. Inside the equations, the trigger, the apparatus, and the animal remained tied together in more than one correlated account. The quietness of the room made the tension sharper. Nothing in the surroundings announced a transition from possibility to fact. The theory had to be told which interaction counted as the moment of outcome. That raised a deeper question about the person making the observation. Some popular accounts suggest that a conscious mind forces reality to choose. That claim goes further than many Copenhagen approaches require. Observation can instead be understood as a physical chain in which one system leaves a durable record in another. Light reaches the eye, electrical signals move through the nervous system, neural activity changes, and a memory forms. Every step belongs to the material world. The person watching is not floating outside the experiment like an invisible judge. That person becomes another participant in the process being described. Once this is accepted, the old boundary grows harder to defend. If the particle, detector, surrounding room, and human brain all belong inside one physical account, then collapse begins to resemble an added instruction rather than an event anyone can point to. It may still describe a real change that current theory does not fully explain. Yet another possibility remains open. The equations may never abandon their ordinary evolution. What appears to be one outcome could arise, because the system, apparatus, and person become correlated in a way that gives each recorded perspective its own result. The measurement problem therefore reaches beyond the question of whether someone opened a box. It asks whether nature truly removes alternatives, or whether each observer finds a history that no longer contains access to the others. If every part of observation is physical, the missing step may not be a new act of selection. It may be a different understanding of what the existing quantum description already contains. Hugh Everett's universe without collapse began with a refusal to add a special rule at the moment of observation. Instead of asking what mysterious event forced many possibilities into one result, Everett asked what would happen if the ordinary quantum equation were allowed to continue without interruption. The proposal was simple enough to state in a few words, and radical enough to alter the meaning of measurement. The same mathematical evolution would govern the particle, the detector, the laboratory, the person watching, and everything beyond them. No privileged boundary would appear when an outcome became large enough to notice. No invisible command would remove the alternatives merely because a human memory had formed. Everett developed this relative state approach in the middle of the last century, when collapse had already become a familiar part of practical quantum reasoning. He did not introduce a new force or a hidden signal. He removed the extra step. Consider a detector that can register one of two possible outcomes. Before the interaction, the apparatus is ready, and the person beside it expects either result. Under collapse, the combined description would eventually reduce to one recorded event. Under Everett's proposal, the interaction produces a larger correlated state instead. One component contains the detector showing the first outcome and a person who remembers seeing it. Another contains the detector showing the second outcome and a corresponding person with a different record. Each result belongs to the version of the apparatus and the version of the observer connected to it. This is the meaning of a relative state. The condition of one part is described in relation to the matching condition of another part. A useful comparison is a pair of ledgers whose entries remain matched line by line. One ledger records the first result beside the observer who saw it. The other records the second result beside the observer who saw that. Neither ledger contains one person remembering both incompatible outcomes. The correlations keep each account internally consistent. From inside the first continuation, one click is heard, one mark appears, one sentence is written into the notebook. The person feels no tearing, duplication, or interruption. From inside the other continuation, the experience is equally ordinary. A different click is heard, a different entry is made, and the person still remembers the same preparation that came before. Both versions inherit a complete local past up to the interaction. Afterward, each carries only the memory associated with its own record. There is no shared awareness hovering above them and comparing the results. There is no single observer who remains central while lesser copies peel away. The formal structure contains several observer states, and every one of them experiences one definite outcome. That is why Everett's idea does not require consciousness to perform a special act. Observation becomes a physical correlation between systems. The particle affects the detector affects the notebook, the surrounding light, and the observer's brain. Each later state contains records that agree with one another. The result feels singular because every local perspective is connected to one coherent account. Everett then extended this reasoning as far as it could go. If laboratories are quantum systems and observers are quantum systems, then the cosmos itself can be described by one universal wave function. There is no external classical realm standing beyond it. Nothing outside the total description waits to inspect the result. The entire physical structure evolves according to the same rule. The popular phrase "many worlds" came to describe the implications of this view, although the wording can suggest a more cinematic event than the mathematics requires. Reality does not need to crack apart like glass. No visible wall suddenly rises between complete copies of a room. The formal description simply develops components whose records no longer agree, with each observer correlated to one of them. Whether those components should all be treated as equally real remains an interpretive claim, rather than a separately isolated experimental fact. The equations alone do not announce which philosophical language must be used. Yet Everett's move exposes a powerful possibility. Perhaps measurement does not destroy alternatives. Perhaps it creates relationships that place every later perspective inside one definite continuation. At the instant before the interaction, several future observer states remain present within the combined description. Afterward, each looks back through an uninterrupted memory and concludes that one result occurred. No version feels like a fraction. No version sees itself as unfinished. Each one occupies a complete account of the event. The cosmos no longer needs to choose between the possible outcomes. The feeling of a choice appears separately inside every continuation that remembers one result. Decoherence explains how a world containing several quantum alternatives can still appear solid, stable, and completely definite from inside one recorded history. Everett's proposal leaves every allowed outcome within the larger quantum state. Yet ordinary experience never resembles a transparent overlap of contradictory events. The detector does not seem to display several readings at once. A room does not appear to contain conflicting versions of the same object. A person does not hear two incompatible answers emerging from the same instrument. The missing piece is the way information spreads into the environment. When a particle interacts with a detector, the result does not remain trapped inside that small device. The detector changes the light reflecting from its surface. It disturbs nearby air molecules. It releases heat, alters electrical signals, and creates physical traces throughout the surrounding equipment. Each interaction carries part of the outcome farther away. Entanglement is the correlation binding those systems together. The particle becomes correlated with the detector with the electronics, and the electronics with the wider room. A result that began as one microscopic event becomes woven into countless physical records. Coherence is what allows quantum alternatives to interfere. It depends on a precise relationship between their amplitudes, much like overlapping patterns that can still strengthen or cancel one another. Once the surroundings become entangled with the result, that relationship no longer remains confined to the system researchers hope to control. The relevant information spreads outward into an enormous number of correlations. Recovering it would require reversing the motion of photons, air molecules, heat, circuitry, and every other system that carried a trace. For a macroscopic object, that task becomes practically unreachable almost immediately. Decoherence is the name given to this loss of observable interference between alternatives. It does not necessarily erase any component from the total mathematical description. Instead, it prevents the components from continuing to produce noticeable cross-effects under ordinary conditions. The alternatives become silent to one another. They remain part of the universal state, but each develops its own network of agreeing records. One detector click is copied into the electronics. The electronics affect a display. Light from that display reaches the walls, the camera, and the observer's eyes. The observer's brain changes as a memory forms. Within moments, the result has become distributed across more physical systems than anyone could hope to control. No conscious witness is required. A stray photon can carry a record. A single collision with surrounding gas can reveal which alternative occurred within a particular component. The environment is constantly performing these interactions, even in a room that appears perfectly still. Imagine two versions of that room after a measurement. In one, the display shows the first outcome. In the other, it shows the second. Both contain the same table, the same equipment, and the same person who entered with the same expectations. Each room appears complete. Each surface feels solid. Each memory agrees with the marks, sounds, and records nearby. Neither room contains a hidden opening through which the other can be seen. Nothing separates them by miles, walls, or darkness. Their separation comes from the loss of any practical way for their records to interfere again. This is why branching should not be imagined as reality suddenly tearing into complete copies at one perfectly defined instant. The structure emerges gradually through interaction. Different components become increasingly independent as information about their outcomes spreads through the environment. A branch is therefore better understood as a stable pattern of correlated records. It contains objects, memories, and events that remain mutually consistent as they continue to evolve. The boundary between branches is approximate rather than sharply drawn. Some interactions produce strong, lasting records. Others leave only weak traces that may still be reversible under carefully controlled conditions. In laboratories, researchers can protect small quantum systems from the environment long enough to preserve coherence. That isolation allows interference to return. Large objects are different because they interact continuously with light, heat, air, and everything touching them. Their alternatives lose access to one another with astonishing speed. Decoherence is a well-developed physical mechanism. The further claim that every effectively isolated component should be treated as a real world belongs to the Everettian interpretation. The mechanism explains why classical-looking records emerge. The interpretation decides what status should be given to the alternatives that remain within the full state. This distinction matters because decoherence does not select one unique global outcome. It does not point to one component and declare the others unreal. It explains why each observer finds one stable record and why incompatible records no longer meet inside ordinary experience. Human decisions are only a small part of this process. Reality does not wait for someone to choose between two drinks, two words, or two directions. Branching is driven by physical interactions occurring everywhere, from scattered light to molecular collisions and electrical changes inside the body. Choices become embedded within that larger web because thoughts and actions are physical events too. The unbroken thread of memory survives because each continuation receives a consistent history. Decoherence does not turn experience into a jumble of competing outcomes. It supplies every later observer with surroundings and memories that agree about what occurred. The result is not a collection of worlds pushed apart across space. It is a collection of records that have lost the practical ability to meet again. Personal identity after branching begins with a person waiting for one quantum result. That person remembers one childhood, one name, one family, and one continuous life leading into the present moment. Every later continuation shares that entire history before the measurement occurs. Nothing in the past belongs more strongly to one successor than to another. Then the interaction leaves different records. One later observer remembers the first result. Another later observer remembers the second. Each inherits the same face, the same habits, the same private fears, and the same memory of standing beside the apparatus moments earlier. From within either continuation, the sense of personal continuity remains complete. There is no sensation of arriving from somewhere else. No warning announces that identity has become plural. The earlier life simply continues into a different next moment. Ordinary language encourages people to ask which version is the original. In Everett's framework, that question becomes difficult to preserve. Both successors possess equal physical continuity with the person who existed before the result. Both contain the same memories up to the interaction. Both can point backward through the same sequence of experiences and honestly say that those events happened to me. Neither carries a visible mark showing that the other is more authentic. The language of copies can therefore mislead. A copy usually suggests that one object came first, and another was produced later as an imitation. Quantum branching does not necessarily provide that hierarchy. The pre-measurement person has more than one future successor, and each one continues part of the same earlier pattern. Consider two letters that match perfectly through every paragraph. The handwriting is identical. The memories, confessions, and promises fill the same pages in the same order. Only the final sentence differs. One ending does not own the shared pages more truthfully than the other. Each completed letter becomes a distinct whole, yet both preserve everything written before the divergence. Personal identity may behave in a similar way. One body does not remain numerically single across several decohered outcomes. There are now separate bodies, separate records, and separate viewpoints. Still, psychological continuity can extend into more than one later person. Memory persists, character persists, expectations, loyalties, and unfinished plans persist. What fails is the assumption that continuity must always point toward only one successor. This creates a sharp difference between the view before and after the event. Before measurement, the person can anticipate several possible experiences. Each possibility belongs to a future observer who will remember being that earlier self. Afterward, every successor finds only one result and naturally describes it as what happened to me. No one experiences the full collection from above. First-person awareness remains local. Each later person knows only the records contained within that continuation. Somewhere beyond any practical contact, another observer may remember the same parents. That person may recall the same childhood bedroom, the same embarrassing mistake, and the same thought held silently before the detector responded. The emotional distance is almost impossible to express. The other observer is closer than a twin in history and farther away than any stranger in access. No message can cross the separation. No reunion can compare the memories. Each successor continues forward, gradually acquiring experiences the other will never possess. Their shared past remains exact, while their futures become increasingly different. These later observers are not distant people who happen to resemble one another. They emerge from one physical history and divide only when their records cease to agree. After that point, each new conversation, decision, injury, discovery, and loss adds further difference. Over time, the versions become distinct people in every practical sense. The deeper question is whether the word you refers to one indivisible object, or to a temporary pattern maintained through memory, embodiment, and perspective. In ordinary life, those features remain bundled together, so the difference rarely matters. In an Everettian measurement, The bundle can spread into several successors. Identity does not move between them like a detachable substance. Consciousness does not select one preferred destination. Each later observer develops from the physical state that came before. The unbroken thread of memory, therefore, does not simply end. It becomes several threads. Each carries the same earlier pattern for a time. Each feels continuous from within. None can feel the instant when the others became inaccessible, because that separation is not itself a shared experience. The physics describes correlated observer states. The claim that they count as the same person, different people, or several legitimate successors belongs partly to philosophy. No experiment assigns an official label to identity. Nature provides bodies, memories, and causal continuity. Human language decides how to group them. Within many worlds, the most unsettling result may be that no single continuation has exclusive ownership of the past. Every successor can honestly remember being the person who stood before the branch. Chance, in a universe where every allowed outcome remains, begins with an apparent contradiction. If every result occurs somewhere within the total quantum state, why should probability matter at all? The answer is that existence and expectation are not the same thing. The many worlds interpretation does not treat every continuation as equally likely merely because each one is physically allowed. The quantum state assigns different amplitudes to different outcomes, and those amplitudes determine their relative weight. Some continuations carry far more of that weight than others. A rare result is not erased, yet it does not become as typical as a heavily weighted one. It helps to picture a fan whose sections are not all the same width. One narrow section may still be present, while the broadest sections occupy most of the spread. A future can be real without being the future a rational person should expect. Before a measurement, the person waiting for the result faces a special kind of uncertainty. That person may understand that several later successors will exist. Each successor will inherit the present memory, the same preparation, and the same expectation. Yet the present person cannot point to one later record and say with certainty that this will be my experience. Probability therefore describes how anticipation should be distributed before the outcome is recorded. After the interaction, every later person finds one definite outcome. A successor in a common branch sees an outcome that appears again and again across repeated trials. A successor in a rare branch sees something unusual and may have no direct way to know how atypical that continuation is. When many similar experiments are performed, the frequencies found by almost all heavily weighted successors follow the familiar quantum pattern. The distribution still reflects the structure carried by the amplitudes. Imagine a long table on which results accumulate one by one. The table stays quiet as each new record is added. A few marks collect in one region, many more gather in another. Rare outcomes remain visible, but the dominant pattern becomes impossible to miss. This is why many worlds does not turn prediction into a meaningless exercise. The theory still indicates which future records should be expected often, and which should be expected only rarely. The deeper difficulty is explaining why those weights should guide belief when every allowed continuation remains in the universal state. The debate remains substantial because probability usually describes which single event will happen, while Everett's framework allows every permitted event to occur. The interpretation must nevertheless recover the same tested quantum statistics rather than assign equal chances to every imaginable event. This issue also changes how personal decisions should be understood. A common misunderstanding says that every hesitation creates a fresh universe simply because a person considered two options. Physical branching does not wait for a conscious choice. It develops through quantum interactions, environmental entanglement, and the spread of records. Human decisions are macroscopic processes embedded inside that wider activity. A choice still matters because each continuation contains consequences experienced by the people within it. One successor may inherit safety, another may inherit loss. Responsible action cannot be dismissed by saying that every outcome happens somewhere. The existence of alternatives does not remove obligation toward the successors who will live through them. From the first-person view, risk remains real because no current person experiences the full distribution at once. Each later version opens its eyes inside one local history. No one is protected by the knowledge that a better continuation exists elsewhere. The total quantum structure may contain every allowed outcome, yet lived experience remains narrow. Probability gives shape to that narrowness. It tells the present person not merely what can exist, but but what kinds of future experience are typical enough to guide expectation. A low-weight future may be real. It may even contain a successor who finds the outcome astonishing. Existence alone, however, does not make that future the one a rational person should expect. Quantum computation begins inside a machine built to delay the outside world. Deep within carefully controlled hardware, information must remain isolated long enough for several quantum amplitudes to evolve together. Heat, vibration, stray radiation, and unwanted electrical signals can destroy that fragile relationship. For a brief interval, the processor must prevent the environment from learning too much about what is happening inside. A classical bit occupies one of two ordinary states. It can represent one value or the other, much like a switch fixed in one position. A Q bit behaves differently. Its quantum state can contain components associated with both possibilities while preserving relationships between them. This does not mean the machine stores two ordinary answers in two hidden boxes. The useful feature is coherence, which allows the alternatives to combine through interference before measurement creates a classical record. A quantum algorithm controls those relationships through a sequence of carefully designed operations. Some computational contributions reinforce one another, others cancel. The process resembles waves meeting under precise conditions, where the final pattern depends on how their peaks and troughs align. The machine gains nothing from merely generating countless possibilities. It must shape them. If every path contributed equally to the final output, the result would contain no useful guidance. The algorithm instead arranges interference so that unwanted contributions weaken while the information connected to useful outcomes becomes more prominent. Measurement then produces a limited classical answer. The processor does not return every mathematical path in a readable list. It yields one result drawn from the pattern the algorithm has created. This corrects a common but misleading description of quantum computers. The machine does not simply try every answer in separate universes and hand them, winning one back. Its advantage comes from controlling amplitudes before the alternatives lose coherence. David Deutsch became one of the central figures in the development of universal quantum computation. He argued that the parallel processes inside a quantum calculation fit naturally within Everett's interpretation. In that view, the different computational components are not imaginary bookkeeping devices. They are physically meaningful parts of the larger quantum state, able to influence the final record while interference remains possible. That interpretation is powerful, but the operation of a quantum processor does not settle the entire debate. Other approaches to quantum theory use the same mathematics and predict the same experimental outcomes. The hardware demonstrates that coherent alternatives can perform physical work together. It does not independently declare that every component must be called a separate world. The laboratory itself reveals how demanding coherence is. The processor may sit within cold, shielded equipment designed to reduce thermal motion and outside disturbance. Signals enter in controlled pulses. The surrounding apparatus monitors minute changes, while engineers attempt to keep environmental traces from spreading too soon. For a short period, several computational contributions remain connected. They strengthen, weaken, and reshape one another without becoming separate readable records. Then the calculation ends. The system interacts with measuring equipment. Information escapes into electronics, displays, cables, and surrounding matter. One classical output appears. The protected interval is over. This brief isolation makes the processor a useful physical example of the same concepts that shape Everettian branching. While coherence survives, alternatives can still affect one another. Once environmental records spread, observable interference fades, and the macroscopic result becomes effectively fixed within each continuation. The machine therefore sits close to the boundary between quantum possibility and classical experience. Inside, amplitudes participate together in one evolving calculation. Outside, researchers see a definite reading and store it in an ordinary memory. No portal opens. No neighboring reality becomes visible on a screen. The importance lies in what occurs before that final record. Quantum computation shows that alternatives within a state are not empty philosophical decoration. Their relationships can be engineered, protected, and used to change measurable outcomes. That fact gives the interpretation debate unusual weight. Whatever language is chosen, the underlying structure must explain how possibilities interfere while coherent, and why only one stable output is later experienced. The processor does not prove that countless worlds surround the laboratory. It reveals how much a quantum system can accomplish before the environment forces its alternatives into records that can no longer work together. Quantum immortality begins with a limit built into first-person experience. A person can remember surviving an event. No one can form a later memory of having no further experience at all. From inside consciousness, continued awareness is always the only condition that can be noticed. This simple asymmetry creates one of the most unsettling consequences ever associated with the many worlds interpretation. Max Tegmark examined an idealized thought experiment designed to expose the difference between collapse and Everettian quantum mechanics. The setup depends on a genuinely quantum event producing more than one physical continuation. In some components, an observer remains conscious and later remembers the result. In others, no later observer exists with a memory of survival. The thought experiment is abstract and cannot be treated as a real test, a source of protection, or a reason to take any risk. Its purpose is to ask what a continuing observer would experience if every allowed result remained within the total state. From the surviving perspective, the sequence could appear deeply unusual. Each remembered event ends with awareness continuing, because only a continuation containing awareness can hold a memory of what occurred. The observer never looks back from a state of complete non-experience. There is nobody there to register that outcome. This produces the intuition known as quantum immortality. If some non-zero component always contains a continuing successor, subjective experience may seem confined to the outcomes where awareness remains possible. The idea sounds like a promise of endless survival. It is not. Many worlds does not introduce a separate consciousness that escapes one outcome and transfers into another. No invisible self leaps towards safety. The surviving person is a physical successor who inherited memories from an earlier state, just as every other continuation inherited the history available within its own outcome. The identity problem therefore remains unavoidable. A successor who remembers surviving may feel entirely continuous with the person who faced the event. That continuity does not prove that one permanent essence traveled between realities. It only shows that memory, embodiment, and causal history continued along that particular component. The distinction becomes even more important when ordinary life replaces the clean structure of a thought experiment. Real human decline is rarely divided into perfect awareness on one side and immediate absence on the other. Aging changes the brain gradually. Injury can damage memory without ending consciousness. Illness can reduce attention, recognition, movement, or personality over time. Countless later versions may continue while preserving very different portions of the earlier person. In a quiet room, the thread of experience might still extend forward, yet the thread may grow thinner. Some memories may disappear. Familiar faces may lose their meaning. The body may continue while the pattern once called a self becomes increasingly altered. Persistence and preservation are not the same thing. A continuation can exist without carrying every quality the earlier observer hoped to protect. That is why the word immortality may hide more than it explains. It suggests an unchanged person moving safely through unlimited time. The Everettian picture offers nothing so simple. A surviving component may carry pain, damage, confusion, or diminished awareness. Its quantum weight may also become extremely small. The mere existence of such a continuation does not make it typical, desirable, or reasonably expected. Probability still matters. Consequences still matter. Every outcome contains real experiences for the people who inhabit it. No rational decision should rely on the hope that another continuation will absorb the cost. For many worlds, interpretation may preserve physical alternatives, but it does not protect any person from suffering within them. Quantum immortality therefore remains a question about perspective rather than evidence of personal invulnerability. It asks whether first-person awareness can ever encounter its own complete absence. It does not prove that awareness must remain healthy, recognizable, or endless. The deepest uncertainty lies in the meaning of continuation itself. How much memory must remain before a successor still counts as you? How much personality can change before continuity becomes only a biological connection? Physics can describe correlated bodies and records. It cannot settle every boundary human beings place around identity. Reality may fan outward without erasing every permitted alternative. Still, each observer awakens inside one local history, carrying only the memories preserved there. No one can inspect the other continuations. No one can know from experience how heavily weighted the present one is. The thread remains visible only from within, stretching forward through whatever form the next moment allows. The most unsettling consequence of many worlds may not be that death disappears. It may be that the self was never as singular, permanent, or separable from reality as it seemed.